I wanted to do one example using the kinematic equations for this rotational motion. So just writing these out on the side, we can relate these angular quantities together for constant angular acceleration. The kinematic equations look similar to what they did look like before. There's just in terms of angles instead of distances in meters. So here we have an electric fan that goes from rest to 2200 RPM. So rest means this initial angular speed is 0. 2200 RPM, just as a reminder, means revolutions per minute. So we do need to convert that. 1 revolution is 2 pi radians. That will get rid of our revolutions. We want this in seconds. So 1 minute is 60 seconds. So let's see, I can get rid of this, one of the zeros, 2 will become 3. So omega, you can find this as a decimal as well. Omega will be 220 pi over 3 radians per second. We want to know the angular acceleration. So angular acceleration is alpha. Now the problem doesn't specifically state constant acceleration, but we have no other information to assume it's not. So in this case, we are going to assume constant angular acceleration. We've been given time. So the top equation will be useful. It starts at rest. Angular acceleration will be omega final over time. Sorry, there's quite the lag on my computer today. 48 radians per second squared would be the angular acceleration. It's going to be in whatever direction the angular velocity is in, but we didn't specifically state a direction. We just know that it is speeding up. So kinematic equations are used the same way we used them before. We do need to be sure the acceleration, angular acceleration specifically, is constant in order to use them. But beyond that, they're fairly straightforward to use, I hope. And so we'll move forward in terms of talking about center of mass and torque, that sort of thing.